Let me just turn the recording on. It's Friday, and we are pretty much approaching halfway through the course here. So I'm glad you're all hanging in there. And today, what I'd like to do is a couple things. One, just spend about 10 or 15 minutes wrapping up energy. So some general comments there. I will use the example of the February freeze that we had here in Texas to make a couple of general points about how I think we should be moving forward, and then we'll wrap that up. Then the plan is to go on to Chapter 4, air pollution. We'll probably get through that, take a break, and then we probably will not get through all of Chapter 5 here today on stratospheric ozone, but at least I can set the scene for ozone depletion. One quick bit of housekeeping, just remember you have a tweet due this evening on renewables. So that's your discussion post for today. Okay, I don't see anything in the chat. Record is on, let's get going. So to wrap this up then, what I've tried to do is give you a sense of the challenges, the sort of maybe not political, maybe more geographic, economic, and environmental challenges, and I suppose opportunities behind the various generation technologies. We certainly didn't have time to look at absolutely everyone in a great amount of detail. So, for example, we haven't talked about geothermal as a particular source, but I think we've covered the main ones, at least the ones that impact us potentially here at home. So some general comments, right? Some general points to wrap this up. One, remember coal remains as a resource the most extensive deposit for electricity, and currently it is the cheapest way of generating electricity. Now, having said that, that doesn't include these externalities like the environmental costs of coal or the health costs associated with coal. But just in terms of getting the material out of the ground and producing electricity, it remains relatively inexpensive, and it's not running out anytime soon. Having said that, the data is unequivocal, right? Here in the United States, coal is on the way out. It's gone from accounting for 50% to about a quarter of our electricity needs. My guess is by the time we get to 2030, that will be closer to 15%. There is no making coal great again, right? And it's over as far as the US. Now, that doesn't mean to say that other countries, in particular China and India and other countries, are still heavily reliant on coal and will continue to expand coal production until such time as we find a viable alternative, right? But if it's not going to be coal, then what are our options, right? Well, obviously, natural gas is a major player here in the US. About 50% of our electricity comes from natural gas. And many other countries as well are not only trying to mine for natural gas as they begin to use fracking technology that has been around for sort of 3 or 4 decades, but there's a lot of controversies around it, right? So you have a proposal in a region to develop a natural gas deposit, and very often you see this kind of response, right? People don't, the environmental lobby does not want fracking generally in their backyard. Okay, so if it's not going to be natural gas, what else are our options? We've talked about nuclear and some of the good, the bad, and the ugly. Remember, nuclear gives you the biggest bang for your buck in terms of an energy source. It operates at a very high efficiency, and I'll show you a graph that sort of summarizes that in just a few minutes. But then, of course, as Matt said early on, when it goes wrong, it goes horribly wrong, and then the economics are problematic, right, for nuclear. All right, so if it's not nuclear, what about hydro? Well, hydro is certainly an efficient and a clean source of energy, but there are environmental impacts, right? So here's a demonstration against a hydro power plant in Indonesia, and I think a lot of people think, well, if we could find the funding to build more large dams, that would take care of us. But many people are against it, right, for environmental reasons. that we just touched on. And, you know, we can go on, right? If it's not going to be dams, then how about wind? Well, we've talked about wind. Wind is a viable renewable energy source. In many states, it accounts for, you know, 10 to 15% or more. Texas is getting close to 20%. Iowa is 40%. Wind is economically viable. It's on parity with natural gas now without any subsidies. Our offshore resources haven't really been exploited here in the United States like they have in Europe. But there's still, you know, a backlash against wind. So my point simply here is that it is extremely complex. People want energy, they want electricity. Obviously, electricity, reliable, efficient electricity is the fundamental underpinning of economic development. At some point, we have to go, okay, you know, which one do we choose? You know, as I said, there's a lot of support in the scientific community for a combination of wind and nuclear being the logical complement. Right now, it really is wind and natural gas in many parts of the world. And again, in Texas, if you think about natural gas is 50% and wind is 20%, you know, 2/3 of our electricity comes from natural gas and wind. But there's a very strong argument being put forward on a number of fronts and from the scientific community that if we are going to keep our carbon emissions in check, in other words, if we're going to argue our energy future needs to be tied and is intimately linked to our impact on the climate, then we probably need to do a complement of nuclear and wind. And, you know, is that viable, right? At least at the utility scale. You know, there was a lot of attention paid in the media, both here and overseas, about what happened in February. So I thought I'd just end off this discussion on energy just to give you my sense of what happened. I had a really interesting Zoom meeting with a number of people in the oil and gas industry and the energy sector. Actually, it was all built in through the MBA here at TCU. Really trying to get behind what happened in February, right? Because if you would put on certain news channels, they were arguing very clearly that all the wind turbines failed, all the solar panels were covered with snow and ice, and that renewable energy was the reason why we went into this catastrophic electricity situation in February. People on the other side of the spectrum argued that everything failed. And that it was because our grid was not winterized. So let me just give you I hope an objective sense as to what happened, and use this just to make a point about the complexity of energy delivery. Let me just look at the situation as of the end of 2020 in Texas here. So we had 50, and you don't have to remember these percentages, but this is versus what was our installed capacity versus our generation in 2020. So in other words, of the total installed capacity of electricity in Texas, just over 57% of the total ability to generate electricity was natural gas, right? In 2020, 51% of our electricity came from natural gas. So we had some leeway there. We had not oversupply, but we had about 6% to play with in 2020, right? Wind, about 21% is installed of our total capacity, but we actually used in 2020, 1/4 of all of our electricity came from wind. So wind continues to grow. Coal, 14.8, we used about 13.4. And so you can see that wind in Texas in 2020 generated twice the amount of electricity than coal did, right? Nuclear in Texas, we generated about 5% from nuclear. Solar, almost 4%. That is growing tremendously. And others like biomass units and hydro, about 2%. So those percentages down the right-hand side should add up to 100%. And I just wanted to, before I show you a couple of really interesting curves, I wanted to give you a sense as to where we got our electricity from in 2020. Does that make sense, everybody? Anybody got any questions on that in terms of what we're looking at there? Okay, so what happened in February, right? So here's what happened in February, and I've tried to do this. I've put a couple of graphs in here from the Energy Information Agency on top of one another. Now these are complicated graphs, so let me show you what we're looking at. So we're looking at a 3-week period here, right? This is February the 1st down at the bottom, starting there. That's February the 1st, and here's February the 22nd over there, right? So we're looking at the first three weeks in February. Okay, this set of curves at the top here, right? These dark blue and mustardy colors. Don't worry for the moment the difference between this yellow and dark blue, right? This is the actual generation, right? The difference is the yellow is the actual generation, the dark blue. So if you just look, let me circle here. If you just look at this period here, you'll see they mirror each other, right? So the dark blue is what was predicted, and the yellow is the actual amount of electricity generated, right? So here we go, and so just think of them as one and the same for now, right? So this is the megawatts over here, right? So you can see we're going through daytime, nighttime, right? Heating and cooling. This is how much electricity is being generated early February, February the 6th, 7th, 8th, and so on, right? The light blue, okay, is what the demand is, right? The light blue is the demand, okay? So you can see we were actually generating more electricity here than when that was being demanded, all right? There was an extension of, an overextension of heating. But the key comes in right here, okay? So here's February the 14th. And all I want to show you here is follow this yellow one here. This is the actual electricity that's being consumed. And the light blue is the demand up here, right? You can see this massive divergence between how much electricity was being generated in total, in terms of how many thousands of megawatts, and what the demand was, right? So the temperatures go down. We get this catastrophic freeze happens, right? Temperatures, wind chills in the -20. And the demand is way up here, right? So we need all of this electricity for heat here in Texas. And what happens is the actual supply, the generation drops off, right? Why does it drop off, right? It drops off because everything fails, pretty much. Let's look at the bottom set of curves here, and this breaks it out in terms of the actual technologies, right? So in green here, that's wind, right? The yellow is solar, the actual generation from solar, right? This is nuclear over here. This straight flat line here is nuclear. Everybody see that, right? That's the actual amount of electricity being generated by nuclear, okay? The brown one here, that is coal, okay? That is natural gas up there, right? And then this little light one down at the bottom here is hydro, and other things, right? So here we're seeing how the grid is managed, right? And so this is managed through an organization, you've probably heard of this, called ERCOT, E-R-C-O-T, the Electricity Reliability Council of Texas. The Electricity Reliability Council of Texas, everybody, does not generate the electron, right? That is the management system of the grid, of all the independent power producers. They look at the supply and the demand, and they say, okay, we've got a higher demand, we need to bring more wind in, we need to bring more solar in, we need to ramp up a natural gas power plant, okay? So when you look at February here, this is the start of the freeze over here, and you look at what happened in February, right? So here's coal, there's the amount being generated by coal, and coal drops from about 10,000 megawatts to about 6,000 megawatts. Coal fails. Here's wind, right? Wind is here at about 6,000 megawatts, and that drops off down there, right, to about 2,000 megawatts, and then it's very low here. Nuclear drops right there, and natural gas goes from there down to there. Everything fails, right? The wind turbines, it's not that wind turbines don't function when the temperatures drop below freezing. They do. You just have to look at Alaska and Iowa and other parts that have much more severe winters. Our wind turbines are not winterized, right? So the gears and the gearbox and all of the lubricants, they're not winterized. So they froze. So wind turbines failed, right? Gas plants failed. Nuclear slowed down, right? Everything because of basically the inability to deliver electrons, everything fails. Solar keeps going, although solar is much lower here, right? Because of the cloud cover. So when you look at what happened in February, about 46,000 megawatts went offline, okay? And that's the difference here between what the demand was up here and what was actually being supplied. That difference, that distance is about 46,000 megawatts went offline because of the freeze, okay? 28,000 of that came from coal, gas, and nuclear, and about 18,000 came from solar and wind. So I just wanted to point that out and make that clear. I know those are complicated diagrams, that the freeze in February, right, and the lack of electricity, we didn't have power for a week, for example. Some people did, some people didn't, okay? That was not because wind turbines froze. That's part of the reason. Everything failed, right, because our grid is not winterized. So any questions on that? I just thought I'd use that as a sort of illustration of the challenge behind the management of electricity. Let me stop there and see if there are any questions. That's just a blow up of that. Okay. So at the end of the day, the quick summary is this. What do we turn to? Okay. As I said, nuclear is the most powerful of all, right? So this shows average capacity factors in the United States by source. Nuclear has a capacity factor of something like 93 to 94%. Right? I hope you're all clear on what that actually means. That means that it's almost operating at its maximum ability, not 100% of the time, but more than 90% of the time, because nuclear, you do shut down to change the fuel out and there is maintenance, right? But look how quickly you drop off here to maintenance and fuel supply when you get to natural gas, coal, hydropower. This is wind in the US, about 34.5 to 35%. This is solar, right? These are the capacity factors. Does everybody understand that? Anybody got a question on the capacity factor here? I hope that makes sense to you now. So when we talk about renewables, okay, so let's just take these two, for example. These are the two most important, right? I get very frustrated when I'm in a conversation with someone and they say, well, we can't use renewables because when the wind doesn't blow, the turbines don't work, and when the sun goes down, the panels don't work. Well, that's absolutely correct, right? 100%. They're not supposed to, okay? It's not magic, it's physics. The point here is that at these capacity factors, let's say you've got wind and solar, and you average those capacity factors out at about 30%, you can, right, generate significant electrons and get those into a grid, but that has to be managed based on the supply and demand, those curves that I just showed you. We have to have, and I cannot emphasize this enough, right? We have to have base load. We have to have some technology that can provide a constant supply of electrons, right, without having to ramp things up and down and up and down. Right now, that base load in Texas comes from natural gas, nuclear, and coal. That's where our base load comes from. And it's dominated by natural gas, 50+%, right? The question is, if we in Texas are operating on natural gas, how much of the sun, how much of the wind, and the other things can we build in, right? So this is critical. The capacity factor is absolutely critical in determining how we move forward. And I know, I don't want to single you out, Matt, but I know you raised an interesting point yesterday when you said, what about scale, right? Everything that I've talked about here at the moment is utility scale electricity delivery, not the distributed in terms of rooftop solar and so on. So the one thing that I think we know without any shadow of a doubt, here we are in 2020, right? So this little diagram shows how many units of energy we're likely to use moving forwards. Don't worry about the scale here, everybody. This is quadrillion British thermal units. It's just a measure of energy, right? This is globally including liquids. Here's 2020. What what is being predicted? Well, this is from the International Energy Association, and they say that coal will probably go up for a while and then level off globally. Liquids will continue to go up. Natural gas will go up. Renewables will go up. Nuclear might go up. The point is that we are going to have to try and supply about 40% more energy by the year 2040 or so, right? That's got to come from somewhere, right? Yeah, certain countries are shutting down coal, but others aren't. And that remains the great challenge moving ahead, okay? So any thoughts on that? And we'll have a nice little sunset slide here when it comes to energy in one of my favorite parts of the world. Again, this is Costa Rica. And why am I showing this? Because Costa Rica, this is a hydropower station. Hydro supplies about 65% of all Costa Rica's electricity. Over here, you can see some wind turbines. They're very important. Just over there, that little area is not cloud. I know it's hard to differentiate, but that's a geothermal plant. And they've also got some solar panels not too far away. So Costa Rica has the geography that can supply renewables. Other places cannot. All right, thoughts, comments, questions, anything? Everybody happy and comfortable with energy? Take a breather and see if there are any issues or thoughts there. All good. All right. Okay, let's move on. Let's move on to chapter 4, everybody. And this is clearly tied up with the search, the exploration, and the generation of energy, the delivery of energy, okay? And that is air pollution, right? Because a lot, I think, of what we read and see and the arguments, you know, pro and con a particular generation technology is couched within, in terms of our air quality. So let me start with this diagram here. I hope this gets some conversation going. What are we looking at? So air quality in the US is monitored by the EPA, right? The Environmental Protection Agency. They have jurisdiction over air quality in the US. And the EPA in the US defines air quality based on one of or all of 6 critical criteria pollutants, which we're going to talk about in just a second, okay? And each of those pollutants has what is known as an NAAQS, right? That's an acronym, and you can see that down here in the legend. The NAAQS stands for National Ambient Air Quality Standards, right? In other words, let's take one, for example. Let's take lead, okay? Lead has a particular standard that is set by the EPA. If a county exceeds that standard, depending on how that standard is defined, whether it's per day or week or every quarter or every year, and I'll talk a little bit about that in a minute as well. If a particular county fails air quality based on one of those pollutants, then by definition, the air in that county is what we call in non-attainment, right? That's a really important term here, everybody, non-attainment. So what are we looking at here, right? This map, and I did this in February of 2021, right? It hasn't changed. I just checked. It hasn't changed since then. So this map shows counties in the US that fail air quality based on either 1 pollutant, that's green, 2 is blue, yellow is 3, this lighter sort of purpley is 4, orange is 5, and this red is all 6 pollutants are exceeded in that count. So now I want to hear from you. You're not going to get off scot-free here, folks. Talk to me about this map. What's going on here? This shows counties with air quality that fail the National Ambient Air Quality Standard. What do you notice?
California's getting a lot more problems.
Okay, Matt, let's start with you.
California's got more than one problem going on.
Okay. So what's going on in California? Anybody from California? in the class? I know we always have students from California. Anyone in California or from California? So what's going on? Yeah.
There's several different reasons, like in California, like they have different violations, like of all the, like, oh, you see all the colors there pretty much. So it seems like
Yeah.
the air there like has a lot of different reasons for being polluted.
Okay, so some of those southern counties have air quality that is so bad they fail based on all 6 of the pollutants, some based on 1, some based on 2, right? What else? This is the type of map you'll see on exam number 2, and I'll just say, talk to me, discuss. There's lots of really interesting things going on.
A lot, you can see like a lot of trends for like cities, but at the same time, like if you look at that like the pink one in California, how it's not like in LA or San Diego or anything. Well, maybe a bit of it is, but like out towards it's kind of like really east.
Okay.
And then there's like little bits like up in Montana that you wouldn't really expect because like
There
no
you
one lives
go.
there.
Okay, Cole, keep going. Yeah, there's a surprise area. Talk to me about other trends. Keep going. What else do you see here? This is what I want to hear.
I mean, you've got like the big like Dallas, Houston area, big like, you know, Newark area. But then there's just a bunch of like really random little areas too, like in the middle of Kansas right there. There's one. There's, like the south of the southern Arizona's got a lot going on.
Okay. Right. And then there are areas like that. Does that surprise you? Why doesn't Miami have an air quality problem? There are 9 counties here close to us that do, 12 counties down in the greater Houston area. So I agree with you, Cole. There's things that kind of intuitively feel right. Yeah, big cities, Chicago, this whole metropolis here that stretches essentially from Boston down to Baltimore. Yeah, and we've got cities here in Cleveland, I guess, and Detroit, Michigan, and those areas. That kind of intuitively feels right. Okay. And then there's Idaho and Wyoming. What the heck? Interesting.
Need those potatoes.
So keep going. Potatoes are farming, right?
Yeah, so obviously most of the stuff that's not in a major metropolitan area is probably due based to either industrial farming or some type of product that they're mass producing.
Emissions of nitrogen oxides and fertilizers. Yep. Yeah. Let's come back to California for a second. What do you think of some of the drivers in California? Ooh, that's a kind of a giveaway, but
yeah, there's a lot of traffic, a lot of
Right.
a lot of periods where you're sitting in the car for a long time with a lot of other people on the highway.
yeah, it's not fun. 2 years ago, I gave a talk at UCLA in LA, and it finished at 4 o'clock, and I had a dinner appointment at 5:30, early dinner down in Irvine. I think it was about a 40-mile drive, and I showed up at 7:30. It was great. 3.5 hours on the highway, right? So what does traffic do? Why is traffic the issue?
Well, it's a lot of people contributing to emissions at the same time for
Right.
extended periods of time.
Okay, so there's emissions, right, coming out from the incomplete combustion from your vehicles, right? So something like carbon monoxide will be pumped out. Yeah, so traffic's important. But I-95, I don't know if any of you have driven I-95 from Miami all the way up through Jacksonville. That's not desperately pretty, and yet they don't have an air quality issue. Huh. Right? So the point here, everybody, is that there's a lot of nuance to whether a particular region has an air quality issue or not, right? And a lot of that comes down to the geography. So we have to talk about the geography. We have to talk about the meteorology, right? Think about this. If you had a line of coal-fired power plants here in central Florida, all putting out pollution. My guess is you probably still would not have an air quality issue in Florida. Why? Why do you think? Think about going to South Beach. You pull up in your Lamborghini and you're sitting on South Beach and you're there for 2-3 days for a vacation. If you're emitting pollution in South Beach, where does that pollution generally go? Pretty quickly.
The ocean.
Bingo, right?
It's funny. I'm actually going to Miami next week.
There you go. You probably won't have to take anything that relates to an air quality monitor. You know, maybe we should send you off with an air quality monitor and come back with a live report.
Yeah, I can check for y'all. My
There you
dad
go.
works in Miami, so he
Oh,
flies
cool.
pretty much every
Okay.
week.
Yeah. All right. Well, so how do weather systems move across the US? Well, they move across the US like this, right? Our storms come in from the west, they ride the jet streams. Generally, airflow across the US is west to east. So if you're emitting pollution here on the Florida Peninsula, most of the time that pollution gets blown offshore pretty quickly, okay? As opposed to what happens here in California. Well, you've got all of this emission, whether it's agriculture in the Central Valley, vehicles going up and down and in and around, right? California, industry and so on. And where does that pollution go? Well, it doesn't go very far because it gets trapped in those valleys. There's something going on in the geography here that helps trap the pollution there and dramatically exacerbates air quality issues, right? And we'll come back and we'll talk about the Metroplex as well in just a little bit. So the where air is compromised, obviously there has to be a human fingerprint there. People, industrial emissions, vehicle emissions, but it is certainly more complex than that, right? So first point is to understand the difference here between what we call primary and secondary pollutants, right? So that's stop number one, primary versus secondary pollutants. So primary pollutants are pollutants that are emitted directly from the source into the atmosphere, okay? So I've tried to sort of summarize here in this little simple infographic. That source can be stationary, so it can be a coal-fired power plant. It can be mobile, like a vehicle. Yeah, there are natural sources going on, but for the most part, primary pollutants are emitted into the atmosphere directly from a source, right? So here are some examples of primary pollutants. NO2, nitrogen dioxide, okay? SO2, sulfur dioxide, a major constituent of coal-fired power plants, right? CO, carbon monoxide, comes out of tailpipes. PM, a really important one, that is particulate matter, fine, tiny little suspended particles, smoke and dust and so on, right? All of those are what we call primary pollutants, okay? Secondary pollutants, which we've got up on the right here, are pollutants that are formed through a series of chemical reactions in the atmosphere. Once you've emitted the primary pollutant, let's just take nitrogen dioxide, for example, that's a primary pollutant. Nitrogen dioxide might react with sunlight, and sunlight could break that pollutant down into nitrogen oxide and an individual oxygen. And an individual oxygen could join an O2, the stuff that we breathe, to form O3. Anybody know what O3 is? O3 is ozone, right? That's a secondary pollutant because ozone forms through chemical reactions in the atmosphere. Here's another one. Let me just change color here. Another one might be sulfur dioxide, right? Sulfur dioxide is emitted into the atmosphere as a primary pollutant, and it may react with rainfall to produce H2SO4, sulfuric acid, okay? So that's a really important distinction right off the bat, is to have this clear in your minds that we've got the emission of primary pollutants, but we've also got the chemical transformation of some primary pollutants, and that forms secondary pollutants, right? And so ambient air quality is looked at both from primary and secondary perspectives, right? Both of these play out. So these are the 6 criteria pollutants that the US uses, and in fact, most of the world uses to determine and to quantify whether air quality is compromised or not. These are the 6 principal criteria pollutants. CO, carbon monoxide, right? A large constituent of the combustion of gasoline. Lead, NO2, nitrogen dioxide, O3, ozone, PM, particulate matter, and SO2, sulfur dioxide. Those are the 6. Incidentally, let me just point this out right here. There are 2 types of particulate matter, PM. We have PM 2.5, and we also have PM 10, okay? Folks, those numbers represent the size of the suspended particles, right? And the unit here is the micron, or the micrometer, okay? A micron. And if you're not familiar with what a micron is, there are 1,000 microns in a millimeter, okay? I know you guys are yards and inches people, but this is all standardized metric. So a millimeter, which is about as thin as a lead pencil, there are 1,000 microns in there. So 2.5 microns you can't see with the naked eye, right? I hope that makes sense. So those are the 6 principal or criteria pollutants. Now, the EPA then has set standards for these criteria pollutants, and I certainly will not expect you, this would be, well, it would be silly to be honest, but I won't expect you to go and remember a table like this and be able to regurgitate what these standards are. But I do want to make a couple of important points. One is, and this is the one we'll just focus on for now. There are 2 different types of standards, right? There are primary standards and secondary standards, okay? So there's primary pollutants and secondary pollutants, but there's also primary standards and secondary standards. The primary standards relate to human health, right? Those are the ones that are the strictest because they directly impact human health and well-being. Secondary standards are more relaxed, but those are important for ecosystem functioning and vegetation and so on. So we're just going to talk here briefly about the primary standard. And my point here, folks, is, again, you absolutely do not have to remember what these standards are, with one caveat, right? And I just want to point this out. I need to update this table. So let's just look at this just to make one point here. So carbon monoxide, for example, right? Carbon monoxide, the EPA looks at in a couple of ways. They can look at it over an 8-hour period, right? So there's air monitors all over the United States. And as long as you do not exceed whatever that standard is, it happens to be 9 parts per million, right? If you don't exceed that over an 8-hour period, at least not more than once per year, then you're okay. If on the other hand, right, you're the mayor of Fort Worth and the Texas Commission on Environmental Quality comes to you and says, well, hey, Madam Mayor, Tarrant County, we measured carbon monoxide on 23 days that exceeded 9 parts per million, right, over an 8-hour period, your county would now be colored in blue, right, as in terms of non-attainment. Does that make sense, right? That's where these standards come into play, right? The reason I just want to, and so, sorry, some of these standards are short-term, like over an hour, some are annual means. Ozone, this has actually now been changed. Ozone is 0.07. That's the only number I would like you to remember off this table, everybody. 0.07 is the parts per million that cannot be exceeded over an 8-hour period, right? So Cole, if I took you and put you on University Avenue with an air quality monitor, right, you would have to stand there between 9 a.m. and 5 p.m. and continually monitor ozone, right? If that ozone stayed below 0.07, right, at all times during the 8-hour period, you're good. Because if it goes over 0.07, then you fail the air quality standard, right? I hope that seems reasonably straightforward and clear. Okay, so here's what's often overlooked, I think, in the sort of environmental discussions, right? What's often overlooked is that air quality in the United States, I think, is, well, it's a bit of a double-edged sword, but I think it's one of the great environmental success stories. So instead of going through each one of these criteria pollutants line by line and bit by bit, which I think would be a bit dull, to be totally honest, what I've done here is plot out the trends in what air quality has done in the US from 1990 through to the end of 2018, okay? I haven't updated this because we're actually still waiting for the 2019 and the COVID 2020 data. And what I've done here, everybody, is I've taken all of the measurements around the US reported for a particular pollutant, right? So let's just take this one here, sulfur dioxide as a primary pollutant. And this data point here in 1990, the average concentrations of sulfur dioxide in the US were at about 55% above the national standard, right? Air quality in the US in 1990 was pretty darn poor when it comes to sulfur dioxide, okay? Ozone were about 25% above the national standard. Actually, in 1990, everything else was less than that. I haven't put lead on here because lead is so far below the standards, you actually can't see it, all right? So lead is of very little concern at the moment. PM 2.5, the light blue, incidentally right here, the EPA only started monitoring that in 2000. So what do you see here? What's the take-home message from the air quality trends in the US since 1990, right? What does it look like? Who wants to summarize the trends? What's the take-home message here, everybody? Air quality in the US, getting better or getting worse?
Better.
By a long way, right? Yeah, absolutely. SO2, 55% above here. We come here through 2018. We are now 80% below what the national standard is. And here's the national standard, right? The national standard is this horizontal dashed line. Everything is plotted relative to the national standard, right? So everything is trending downward, right? i.e. the air is getting cleaner. The problem is this one, right? Ozone. Ozone remains our real challenge here in the US, right? So I think that's often overlooked. Here's an example, right? This shows the concentration of nitrogen dioxide in 2005, and then 6 years later, as a result of stronger implementation, or better implementation, if you like, of legislation, okay? So anything in red shows high concentrations of nitrogen dioxide. Anything in light blue shows lower, right? Here is a significant improvement in the nitrogen dioxide concentrations. And if I go back to this diagram for a second, nitrogen dioxide, let me just annotate this quick. Nitrogen dioxide is this one here in green, right? And here's 2005, and here's 2011. We're looking at that trend right there, okay, in this next map. So nitrogen dioxide is improving, as are many of the other pollutants, right? But here's the two sides of the coin. Here's the double-edged sword for me, everybody. That is, when we look at the number of people in the US that are living in counties that fail the national standards, right? Lead is almost no issue. Nitrogen dioxide, we're good. Carbon monoxide, we're good. Sulfur dioxide, we're much better, right? Particulates are problematic in some counties, and it's dominated by this one, ozone, okay? So let's focus in here for a little bit on ozone. What do you folks know about ozone? When I say ozone, what jumps to mind? Let's just get some things out on the table here. What jumps to mind with ozone, everybody?
The ozone layer in the atmosphere.
All right, I'm really glad you said that, Jacob. Ozone layer in the atmosphere. What else? Why did you say that? That's an important one.
That's probably the only time I really ever hear about ozone.
Okay, good. Cool. Right? Anybody else? What about, I saw this the other day. I was driving down I-30 and I saw one of those big electronic billboards. And it said, today is a level orange day. There is an ozone alert out there. Anybody ever seen that? Mm-hmm. So Jacob, that has nothing to do with the stratospheric ozone layer that you mentioned, right? And so I'm glad you mentioned that, because this is a really, really key distinction. And it's why indeed there is a whole separate chapter on this. So there are two different types of ozone, just to make things nicely confusing. okay? So there's ozone that occurs in the stratosphere, right? So that's the next layer up. That's where Richard Branson was playing around with the other day in his Virgin Galactic aircraft, right? The stratosphere is the next layer in the atmosphere. That's where ozone sits, and it protects us from ultraviolet radiation, right? That is not the type of ozone that we're looking at on the screen here, right? This is lower level ozone that occurs where we are in the troposphere, and it is a human-made pollutant, right? So there is a fundamental, absolutely fundamental difference here between ozone in the stratosphere and ozone in the troposphere. Ozone in the stratosphere is created naturally and acts as a protective shield from ultraviolet radiation. Ozone in the troposphere is created by humans and is a pollutant, right? The challenge, everyone, is that chemically they're identical, right? It's O3. It's made up of 3 oxygen atoms bound together, but they perform completely different functions. They form very differently. So the ozone that we're talking about here and that you see on this diagram is low-level ozone, the human-made pollutant. We're going to come back and talk about stratospheric ozone in chapter 5. Is that clear? Does that make sense to everybody, or is anybody still a bit bamboozled by that? And it's absolutely okay to be, because it seems odd that we've got a chemically identical substance that produces, that has 2 different effects. All right, so here's the situation with ozone. This was March 2020, right? These are the counties in the US that are in non-attainment when it comes to ozone. So this classification, the light blues are marginal, all right? Ozone was problematic in March, right? As you get into the purples and the longhorn oranges, we're getting into more severe and extreme, okay? Again, California shows up as very problematic air quality, but you can still see these counties in the Metroplex and Houston are in non-attainment. So it mirrors in many ways the map that we just saw, right, at the outset. We don't see the intense agricultural emissions that Matt, you commented on in that first map here, right? Because ozone is a human-made pollutant, right? So we need the emissions of primary pollutants that then get converted into tropospheric low-level ozone, okay? All good. So here's my attempt at a simple graphic to make this clear that we're looking at 2 different types of ozone. Both of them are O3. One occurs in the stratosphere, that's the protective ozone layer. One occurs in the troposphere. That's the low-level smog and the pollution that is associated with non-attainment and problematic air quality. Another way to think of this, some people like this little phrase, good up high, bad nearby, right? Good up high, protective from ultraviolet radiation. Bad nearby, it's a pollutant, okay? So how does it form, okay? How do we actually get ozone forming as a human-made pollutant? So let's just look at one example. We'll start at the bottom left here. So NO2, right? This is the one I pointed out just a few slides ago. NO2 is nitrogen dioxide. That's a human-made pollutant, right? And nitrogen dioxide then gets emitted into the atmosphere, say from a coal-fired power plant or a cement factory or a waste incinerator. Okay? Sunlight then disassociates that or splits that apart and isolates an oxygen atom off that NO2, leaving NO and the individual oxygen, and that individual oxygen joins up with the O2 to form O3. Human-made. Why? You got to emit the primary pollutant, that gets converted chemically in the atmosphere to the secondary pollutant, right? And another source of the primary pollutant are these things called volatile organics, right? Volatile organic compounds are a range of exactly that, compounds that are volatile, they're problematic, and they interact with sunlight. And this oxygen here from the VOCs that come from commercial processes and motor vehicles, that oxygen then gets isolated, joins the O2 to form the O3. So I cannot stress that enough, everybody. It's a human-made pollutant. And again, I'm not going to ask you here the exact percentages of where these come from. Just take a look at these 2 pie charts. You can see the sources of nitrogen oxides like NO2, motor vehicles, utilities, industrial, commercial and then volatile organics dominated by industrial commercial processes like cement factories and waste incinerators, but also motor vehicles, right? So that's why there is a very, very powerful, strong human footprint when it comes to tropospheric ozone. Okay, so here's a diagram of ozone in Houston. This was just a really interesting period. So this is June 2011. Now, how are we doing on time? Okay, I'm going to go for about another 10 minutes, and then I'll give you a break at 9 o'clock. Because I don't want to lose a train of thought here. So here's what the EPA in the US does, and in fact now most countries around the world subscribe to this, okay? Instead of someone coming on TV on your 6 o'clock news and saying, hey, good evening, everybody, I'm going to talk about air quality here in downtown Houston for the moment. The ozone levels are 0.061387 parts per million. They're going to be going up to 0.7128 parts per million by midnight, right? Most people would go, I don't know what that means. That doesn't make any sense to me. So we have this thing called the AQI, the Air Quality Index, right? And the Air Quality Index is a really, really neat, simple way of expressing air quality, okay? And how does it work? Well, they take the Air Quality Index and they take the ozone level, right, the primary standard. So they'll take that 0.07 part per million and they'll say, if your measurement right now is below that, it gets green. It's good. Your air quality is good. It gets a similar scale, but just from a 0 to 50, right? If your part per million begins to go over that national standard, then they will issue a level, a yellow level, right? So between 50 and 100, your air quality is moderate. From 100 to 150, your air quality as it relates to ozone is problematic for certain groups, right? The AQI, the Air Quality Index, is this very, very simple, rather elegant color scheme that is normalized to the primary standard, right? And I think most people can get their head around, you know, if your air quality right now is 200, that means it's problematic and it's purple and we're in trouble and you better stay inside, right? So when you're driving down the highway and you see the billboard light up and it said, today is a orange ozone day, what that simply means is that the ozone levels are down here somewhere between 100 to 150. Does that make sense to everybody, right? And so what you're looking at here is the Air Quality Index expressed at this particular time for Houston, right? So anything that lies out here in the yellows is moderate, and anything in the oranges here are unhealthy for sensitive groups, and downtown Houston problematic. So what's going on in Houston here? Why are you looking at a map that looks like this? I don't know if anybody's from Houston. Why are these 12 counties in the greater Houston-Brazoria area problematic? Why do we have an ozone issue here on this particular day? June the 6th. Oh, that would make a nice exam question.
The weather.
Claire.
Oh, the weather.
A little more, Claire. What about the weather?
I know that the different temperatures can affect the ground ozone
Why? Exactly.
pollutant.
Exactly. So the hotter the temperature, the more problematic the ozone, right?
Yes.
Why? Nice observation. Why is temperature a control here? Generally. Because how's ozone formed? You emit the primary pollutants, and then what do you need to break down the primary pollutants? You need?
Sunlight.
Yeah, sunlight, right? So Claire, you emit the primary pollution, the nitrogen oxides and the volatile organics, and the more sunlight you have, the more intense sunlight, i.e. the hotter the temperature, that speeds up the breakdown process of the primary pollutants, freeing up the oxygen that can then form ozone. Does that make sense? Right? So ozone is often thought of as a summertime pollutant. It's not exclusively, because you can have a lot of emission of the volatiles during colder periods, but it's generally speaking a summertime pollutant. There's something else going on in Houston here that's exacerbating the problem. So we've got lots of cars My wife's from Houston. She's an Astros fan. She's like, honey, if you can drive in Houston, you can drive anywhere on the planet, right? Crazy. But lots of cars. And what else do you have in Houston that might be exacerbating the air quality issue besides just vehicles? Do you think?
Humidity.
Say again, Mackenzie?
Humidity.
Okay, yeah, it is stinky humid, but that doesn't play in here. Think about chapter 3, energy. Anybody driven out here on I-10, past Trinity Bay, up to Beaumont? There's something going on here. What's going on here? Keystone XL. Anything ringing a bell? Come on, young environmentalists. What's coming down this pipeline from Canada?
Oil.
Oil.
So that area is
Yeah.
a large gas and oil factories.
Yeah,
Beaumont's
petrochem-
notorious for it.
yeah, the petrochemical refineries, right? The most sophisticated petrochemical refineries essentially in the world here, okay? Bringing all of this oil down from Canada along the Keystone XL, and of course being brought in through the Gulf of Mexico, right? Those petrochemical refineries are putting out the volatile organics and the nitrogen oxides, okay? So it's not just vehicles, it's also what's being done nearby. Okay, so I know I'm running a little longer than the normal coffee break, but hang in here because I want to cover a couple other things. Let's just turn to California for a second. Folks, the geography of the region is critical, okay? There's a reason why in California, the Central Valley is so enormously problematic, right? So here's San Francisco over there, here's LA over there. Again, I don't know if any of you are from this part of the world, but what is this? This is the Central Valley in California, right? What is it surrounded by? Mountains. Why is that important? Well, because what happens is the cool air drains down the valleys down the mountainsides into the valley. And that leads to this phenomenon that I've on the right-hand side here, right? This leads to the development of what we call inversions. So what's an inversion? An inversion is a meteorologic phenomenon where your temperature up here is warmer than the temperature at the ground, okay? I don't know if any of you have ever experienced that. If you're driving along a road and that road goes downhill into a valley at night, especially in winter, it's much colder down there, right? We tend to get fog down there and clouds forming down there because the cold air drains and the warm air stays above. Why is that a big deal? Well, what an inversion does, everybody, the inversion acts essentially as a lid, and any pollution that is produced below that inversion has a really tough time escaping. Here is a rather grainy iPhone photograph I took back in 2013. There's the Hollywood sign over there. I'm standing at the Griffiths Observatory, and you can see this, right? This kind of hazy smog that's sitting there, that's the pollution that's being trapped below the inversion. Now, it's not just in valleys, because we often have that in the Metroplex here. I don't know if you've flown in DFW and you'll see it's kind of a smoggy winter's day. That is sinking air that's causing the inversion sitting over a particular region, right? My point simply here, everyone, is that it's the geography and the climatology of that particular region, right? That is enormously problematic. Of course, the other thing that's often overlooked here in California is what goes on in the Central Valley here. The Central Valley produces some of the most important food in the United States. About half of all of our vegetables come from the Central Valley. So we've got intensive agriculture, and what are they putting on those fields? They're putting nitrogen fertilizers on those fields, right? And it's the emission of the nitrogen coming out of the fertilizer that's then getting changed and converted into ozone. So very, very complicated picture, right? Okay, finally, let's just wrap up this section here. This shows the AQI, right, in a little more detail. I only want to just make this one point here. Let's just look at ozone for a second here. So ozone, if your levels are between 0 and 0.059, then you're in the green. If you're approaching the standard, that standard has been changed now to 0.7. Then you're in yellow. And as you go on down here, it gets worse and worse and worse. You can look at air quality based on one pollutant, or you can average them across all the pollution. right? Worldwide, generally speaking, pollution, air quality and pollution worldwide is defined by looking at particulate matter, right? PM 2.5 and PM 2.10, but we'll come back and talk about that. So here's the good news. Remember, this is a double-edged sword, right? The good news from an air quality perspective is that, and I've tried to plot this, I know this is a really odd looking scale here, everybody, but we've got 1970 to 2000 to 2010 to 2018. So I've kind of scrunched up 1970, 80, 90 to 2000 and then expanded out the last 2 years. And I have plotted the relative change here in GDP, the number of vehicle miles traveled in the US, population in the US, energy consumption in the US, carbon consumption in the US. See, CO2 has gone down. That's a discussion later on. But from 1970 to 2010, all of this is going up. And yet, when you look at the aggregate emissions from all 6 of the criteria pollutants, in other words, if I was to take all 6 of those and average them out, our air quality has improved dramatically here in the US, right? We have some of the best air in the world, which may seem odd when we look at how we still struggle with ozone, right? The final thoughts I want to leave you with before I do let you on this little coffee break here is we're going to come back and be able to review, I think, in a bit more detail, not in this course, but it'll take a bit more time, just how COVID impacted air quality, right? We saw this around the world. Now, I would never advocate that we need pandemics to address our environmental issues. But nonetheless, this pandemic, I think, has given the planet an opportunity just to pause. This shows the average concentrations, right, of nitrogen oxides here from March 2015 to 2019. So this is nitrogen dioxide. This is what on average it looks like in the Northeast, right, over that 5-year period. This was the nitrogen oxide concentration in March 2020, right, whilst the Northeast was in lockdown. Take a look at this diagram. This is another way to look at it, right? Here's the Central Valley in California. So we've got LA at the bottom, San Francisco up here, and I've got through 4 different phases from pre-shutdown, and this again is nitrogen oxide concentration. So we've got pre-shutdown 2 to the 6th of March, all the way through to complete shutdown at the end of the month. Look what happens in LA, okay, down here, relatively speaking. Look what happens along the main highways here in the Central Valley in terms of nitrogen oxides, okay? And we saw this in Beijing, we saw it in Paris, Madrid, around the world, right? In terms of cleaning up air quality. So, interesting. Okay, let's take a quick break. We'll come back at 9:15, everyone. Take a coffee break. I would like to just talk a little bit here at the end about air quality worldwide. So I'll spend 10 minutes just sharing a personal anecdote here, a little personal story. All right, folks, back. I have my vanilla latte and we are ready to go. Okay, let me spend 10 minutes or so talking about air quality from a global perspective. And then we will switch over and I will begin the material on chapter 5. Just as a side note here, there is a section in chapter 4 on acid rain. I'm going to just park acid rain to the side for the moment. Let's just leave acid rain and see if we have time at the end of the course to come back and address that. And part of the reason for that, just to be totally honest with you, is I read an article in the New York Times this weekend, and the title of the article was, I wonder whatever happened to acid rain. Acid rain was actually kind of the most prominent environmental issue in the 1980s. Much more so than climate change and global warming. But we have actually done a remarkably good job of not completely controlling acid rain, but going a long way towards putting it in that sort of bucket of environmental success stories. So I'm just going to make a kind of on-the-fly decision here to park acid rain for the moment, and we'll see if we have time to come back to it. If we take a step back here from the US for the moment, so we've talked about air quality in the United States, right? And ozone remains our biggest issue for sure, and that deals with the geography of the region, but also the emissions of the volatile organics and the nitrogen oxides and how those two pollutants form and compromise air quality dramatically in many counties here in the United States. Globally, particulate matter is of greater concern. Now, that's not to say that ozone is of no concern, not at all. But here, when we look at global air quality, much of that focuses on particulate matter and PM 2.5, right? The finest particles, because those are the ones that can get into your respiratory system and penetrate the deepest into your lung systems and really compromises health around the world. So this little diagram here looks as a global summary. The World Health Organization guidelines for particulate matter is 10 micrograms per cubic meter or less. So there's just a new number to bear in mind here. 10, 12 still keeps air quality in what the air quality index would define as good, right? So the World Health says 10, the air quality index is 12. I'm not going to lose sleep over either of those. Bottom line is, if your air quality is in the blue or in the green, on average, as an annual average, your air quality is by definition good. So here's the global map. There are clearly countries where we don't have good, reliable data from, and you can see much of Africa falls into that, right? Air quality in Scandinavia, North America, Oceania, especially Australia and New Zealand down here, and you include countries like Germany, the United Kingdom, Japan, and so on. Air quality is generally pretty good from an AQI perspective, at least as it relates to PM 2.5, right? Challenges, and again, just bear in mind, there's a lot of missing data here where we just don't have good, reliable information. But the real significant challenge globally at the moment is this part of the world, right? South Asia, which is basically India, Sri Lanka, Pakistan, Southeast Asia, Indonesia, Malaysia, right, Borneo, and East Asia, which includes China, right? So this is where a huge concern rests. And remember our population discussion, there are more people living inside this circle than living outside of that circle, right? So when I think it comes to global air quality, we often tend to think of perhaps China as being the most compromised, right? And I showed you the example of Beijing during the Olympics. But in fact, the world's most polluted cities, and these are the top 10, right? And these are annual averages, incidentally. These are the world's most polluted cities. You can see of the top 10 cities, only one is currently in China, right? Just marginally behind Ghaziabad in India, okay? Delhi in India is the world's most polluted capital. So you look at these numbers here on the index, the PM 2.5, and I've put here the most polluted city in the United States when it comes to particulate matter, right? And other large cities for reference, okay? So Dallas is right on that, just above that 12. So by definition, it's moderate. So DFW is 12, LA is 12.9. Portola in California in the Central Valley is 16.9. You know, these top 4 or 5 cities are all above 100, right? Just incredibly compromised air quality. And the Prime Minister of India, Narendra Modi, has come out and said he realizes quite clearly that this is a threat to the economic development because it's an enormous threat to the health of India's citizens. Just anecdotally, I just wanted to share this little story with you. I was in India in 2017, November of 2017. I was giving a paper at a conference in New Delhi, and I flew into New Delhi on Sunday night and landed at midnight, and it looked really, really foggy. And when I woke up in the morning, on the Monday morning, early, and I went down for breakfast in my hotel, it was foggy inside the foyer of the hotel. It turns out it wasn't fog, right? It was pollution, particulate matter. This was the headline of the paper on that morning, right? Delhi gasps for breath. Air quality is in the severe category, right? I wasn't really aware of what was going on. I just simply was tired and not paying attention to the point where people were walking around. It looked like COVID, right? People were scrambling to try and find masks. I went out later that day to try and take in the sights. The conference only started on the Tuesday. And this was this was taken at 1:30 in the afternoon, right? At one of these beautiful buildings that you could only just make out because of the pollution. So it was an extraordinary experience being there for 3 days. Several of the airlines, including British Airways and United, shut down their flights into Delhi. The air was so compromised. And what I'm about to show you is a map of New Delhi showing the air quality, right? Now, remember, the colors are, green is 50, yellow is 50 to 100. The reds are sort of 150 and above. This was the air quality index in New Delhi, right? on that Tuesday morning. I mean, it was absolutely unbelievable. My hotel was just about here, and the air quality was not measurable. It was 999. In other words, it was basically above 1,000, and they couldn't really even measure it. It was so incredibly polluted, right? So this was actually on the Wednesday, not on the Tuesday, but on the Wednesday. And the culprits were particulate matter, PM10 and PM2.5. You can see the air quality index for ozone was pretty good. Nitrogen oxides were a little compromised. SO2 was not a real concern. Carbon monoxide was some concern, but it was particulate matter, right? That was compromising the air quality. It was like a thick soup, which then gradually cleared up. And the reason, and a lot of people think, well, Delhi has, 20 million plus people, which it does, right? Which is extraordinary in and of itself. So here's New Delhi over here, the capital city. It has as many people as the entire state of Texas. And what was to blame here? Well, it was smoke pollution from the burning of crops. And this is an extraordinary thing that happens every October and November in this part of the world. So all of these red dots that you see around here, I'm kind of circling them in green, more or less, right? These are fires, and it's fires from the burning of crop stubble, right? The residual leftover of the crops, the stubble burning. And all of this kind of white, foggy cloud area here, this is all the pollution, right? This is all the particulate matter pollution. And this is the foothills of the Himalaya mountains. So this is an extraordinary situation that is set up every October and November. Cold air begins to drain down from the Himalayas. So you've got cold air coming down here, which leads to an inversion sitting above. And then you've got all of these fires that are being created through the burning of crops. And it causes this catastrophic air quality. And the Indian government is doing all it can now to try and relieve the situation. So I just wanted to end there with that little anecdote, because when we talk about air quality and compromised air quality in the US, yeah, there are certainly parts like California and where we live here in Texas at times of the year where the air is compromised. But it doesn't come close to what other people are experiencing around the world. All right, so let me stop there. Oh, and you know what? I'm going to just do another share here real quick. Let me try and make this a little more. Yeah, here we go. This is a really neat, I hope this website has come up, right? This is a really neat website. It's WAQI. It's the World Air Quality Index. I hope you can see this. Whoop, let me just shut that down. Are you, let me ask you who's up on my screen. Matt, I see you on my screen. Are you looking at the website for the World Quality Index at the moment?
Yes.
Okay, cool, thank you. It's really neat. It's real time, and it shows air quality monitors around the world, right? It's got the color, so you can see the air quality scale on the bottom here: good, moderate, unhealthy. This is particulate matter. You can change the particular pollutant, right? So this is the general AQI. You can change it to PM, right? Small particles. So if we just went to PM and changed it to small particles, you can see small particles in the US not a concern right now. Small particles in Southeast Asia still a real concern. But let's just go back to air quality. You can see how Africa just simply has such a dearth of monitors and information. South Africa is still pretty good from an infrastructure perspective, right? There's the US, some compromised air quality here. What's going on up here, right? This heat dome and the residual heat, and still some fires up there in Canada. Let's come down here and look at what's going on right now. I know we're not in the peak season for air quality, which is October, November. but you can see right now there's still some parts, 832, right? This is Taltora in Lucknow, India, a PM 2.5, really, really high at the moment, right? Japan, Okinawa, pretty good. It's a really neat website. You can go into any city around the world and check the real-time AQI, just incidentally. And well, let's bring it back close to home here real quick. Let's see where we are right now. The Woodlands, Dallas, Fort Worth, Midlothian, Fort Worth. It's all good. Air quality is pretty good at the moment. No issues outside. Right, what's going on here? Centro Piedra, Mexico. Ooh-wee. What do you think's going on down here? There's something going on right on the border of Mexico here, which is making air quality hazardous at the moment. There's a gigantic coal-fired power plant system there. All right. I thought that would be a useful reference for you if you were doing any work or were interested in checking air quality around the world. All right, everybody, let's see what questions we have there. Anything on air quality before we move on? Where are we at? 9:30. Perfect. All right. Okay, let's go to this stratospheric ozone. So here we move on onto chapter 5 into stratospheric ozone. And there is, so this material comes with a warning, if you like, not a bad warning, but just something I need to make you aware of. This material can be a little more complex, right? Because there are two aspects to talking about stratospheric ozone, right? One is kind of how it was discovered and what it does and where it forms and how it forms, the story of the hole in the ozone layer. And that's pretty straightforward. And, you know, I'm a nerd, so I think that's a fairly interesting story to tell. There's another aspect that's a little more complicated, right? And the slightly more complicated aspect is that I want you to understand in a little more detail the chemistry behind what goes on here, right? Because not only is it an interesting story, I think it's fascinating to look, and we'll look at real time, not today, but on Monday, we'll look at real time what's going on over Antarctica. There's an incredible set of things that happen every year that are of significant concern in terms of stratospheric ozone. So there's a little bit of chemistry here, and I'll be very explicit, folks, what I expect you to know for the exam, okay? So that's kind of where we headed on stratospheric ozone. So my goal this morning, just for the final 20 minutes, is to tee this up for you, to set this up in terms of the context before we get to sort of unpack stratospheric ozone. All right, just as a reminder, okay, we're dealing with two types of ozone here. Low-level ozone, which we've just talked about, that's a constituent of pollution, and it's a pollutant in and of itself. It's a human-made pollutant. And then there's the stratospheric ozone, right? Here's a slightly more scientific way to look at it, right? Important diagram here. So this shows altitude, both in miles and kilometers here. And I just want to make a comment here about this axis. So this shows the vertical distribution of ozone, right? On average, around the world, if you were to take a weather balloon and you were to send that weather balloon up from the surface, and the monitor that was measuring ozone was dangling off the bottom of that balloon, this is more or less what you would find in terms of the vertical distribution of ozone. And the scale here is in millipascals, right? So all of the constituent gases in the atmosphere, the nitrogen, the oxygen, the carbon dioxide, the methane, the water vapor, the argon, all of them, right? All of those gases are exerting a pressure down on the surface of the Earth. And ozone is also exerting a pressure, but the amount of ozone is tiny, right? It's a fraction of the atmosphere. So we express it in millipascals. This is really, really small in terms of atmospheric pressure. So that, just bear that in mind, okay? So when you look at the vertical distribution of ozone, it starts off here at the surface, okay? And it decreases with altitude. So as you go up through the first 2 to 3 miles or 2 to 3 kilometers, your ozone concentrations go down. This here, everybody, is the surface tropospheric ozone that we've just talked about, right? The human-made ozone that's going on over Texas and Houston, okay, right now, right? It only accounts for about 10% of all of the ozone in our atmosphere. Then ozone is pretty much mixed vertically as you go upwards here. And then when you get to about 15 kilometers or around about 10 miles, your ozone concentrations go up dramatically. They reach a peak here at about 12 to 15 miles, 20 or so kilometers, and then they go down like that, right? That is the stratospheric ozone, right? That's about 90% of all the ozone in the atmosphere, okay? And that's the focus for chapter 5. That's where we go to, the stratospheric ozone. This is bad, human pollutant. This is good. It's a protective shield, okay? Makes sense to everybody. That's a really critical diagram. And the one thing that I think is also important to note here is that when we think about ozone in the stratosphere, this protective layer in the stratosphere, it's not a thin layer like that is literally putting, like putting a lid on a boiling pot on a stove. It is dispersed throughout the atmosphere here, from about 10 miles to about 15 to 18 miles, right? So it's not a thin cap. It's a layer that is dispersed throughout the stratosphere. It just reaches a peak concentration right at about 12 to 15 miles, something like that. I hope that's clear in terms of what we're looking at. All right, now, here's my challenge, right? My challenge with this material in stratospheric ozone, it's a bit like a chicken and an egg, right? There's a simple way to deal with this, and then there's a slightly more complicated way, which unfortunately I'm going to have to deal with because I want you to understand this process. So let's start simply here, right? Let's just talk for a minute about the formation and the destruction of stratospheric ozone, right? Formation and destruction. And let's start with ozone that is formed and destroyed naturally in the stratosphere. Okay, so I've drawn these as individual oxygen atoms. Here's an O2, diatomic oxygen, and then here's an ozone molecule, right? So first off, everybody, how is stratospheric ozone formed, right? It is formed naturally in the stratosphere. How? Step one, O2, right? Diatomic oxygen, the oxygens that you and I breathe, okay, which are there in very, very small concentrations in the stratosphere, okay, but it's there. That oxygen is split apart by sunlight into individual oxygen atoms. And those individual oxygen atoms can find an O2 and join up to form an O3. That is a natural process. Okay, we have no role to play in that process. Does that make sense? Right? So oxygen O2 that's sitting there in the stratosphere is broken apart into individual oxygens. One of those oxygens will find an O2 to form an O3, right? Natural process, okay? At the same time, right, ongoing continuously is that sunlight will split apart the O3s into individual oxygens and diatomic oxygen. That is an ongoing, continual, simultaneous, contemporaneous process. Those two are always going on all the time in the stratosphere. Oxygens are being destroyed and the individual atoms are forming O3s, and O3 molecules are being destroyed, freeing up individual oxygens and diatomic O2, right? That's point number one of the whole discussion of stratospheric ozone. I really need you to be 100% happy and clear with that. Any questions on that? All good. So over time, what has happened is that we have built up this background concentration of stratospheric ozone, right, in the stratosphere, that second layer of the atmosphere, the layer that occurs above the weather, right, the layer that occurs above where airplanes fly, right? We've got this background concentration that is built up over time. So what does it do? It protects us from harmful ultraviolet radiation, right? Now, I think what's, to me, fascinating about it is, even though that stratospheric ozone is distributed and dispersed through the stratosphere, the amount that is there is really, really small, okay? And how do we measure it? How do we express stratospheric ozone? Well, we measure it using an instrument, and we express that with something called the Dobson unit, right? So temperature is Celsius or Fahrenheit, right? Pressure is millibars or inches of mercury. Ozone is always expressed in the scientific world in terms of the Dobson unit. And this is named after George Dobson, the scientist who developed the instrument to actually measure stratospheric ozone, right? So how does this work? What is the expression of ozone, okay? So if we were to be able to take, so I'm just going to try and draw this up in the top right-hand diagram, that first diagram of ozone here and altitude here. So we've got that little bit of surface ozone, and then it wiggles up here, and then here's the stratospheric ozone, right? That diagram I showed you at the outset. If we were able to compress all of this ozone in the stratosphere, if we were just to physically be able to compress that down, okay, it would form a layer just 3 millimeters thick, okay? To me, that's mind-blowing, right? All of that stratospheric ozone would form a layer 3 millimeters thick. That would be thinner than this little power cord that I'm holding up here, right? This is about 4 millimeters over here. That is what's protecting us from being fried, essentially, okay? Absolutely remarkable. So 3 millimeters is the thickness of the ozone layer if, which we cannot do, but if we could compress it down, it would be the equivalent of putting 2 pennies on top of one another, right? Okay, so what does 3 millimeters of ozone look like in terms of Dobson units? We express that as 300 Dobson units, right? In other words, 1 millimeter of ozone is the same as saying 100 Dobson units. Guys, this is the number I want you to remember here, right? 300 Dobson units. Okay? That's the number I would like you to remember. Why? Because 300 Dobson units is what we consider to be average ozone in the atmosphere, right? So if we were to talk about, well, what's a good average? 300 Dobson units is considered the average concentration of stratospheric ozone, okay? It varies depending on where you are above the planet, but that's a good number to remember, 300 Dobson units. So just kind of imprint that in your minds, okay? And so what's the big deal, right? What's the big deal with this 3 millimeters or 300 Dobson units, okay? So this is a little bit of the chicken and egg rearing its head right here, okay? So we get our energy from the sun, right? You all know that, okay? So the sun sits out there and is basically this gigantic nuclear explosion, and it sends out energy to us, right? It sends it out throughout our solar system, but it sends it to us in the form of radiation, right? Those particles that travel through space have different wavelengths, okay? And I'm going to come back and talk about the electromagnetic spectrum and wavelengths and all of that when we deal with climate change next, right? But for now, all you need to appreciate is that we get this energy from the sun, and some of those wavelengths are these short, very intense, rather dangerous ultraviolet wavelengths, right? Now, when you, hopefully you don't, but when I broke my ankle, I had to go and have an X-ray, right? What's happening is they're firing radiation at your ankle, and those wavelengths are even shorter and more intense than ultraviolet, right? So ultraviolet comes into us from the sun, and there's actually 3 types of ultraviolets. Guys, don't worry about these numbers here for the moment. I'm going to come back and refer to those when we look at the electromagnetic spectrum. But for now, just appreciate that there are 3 types of ultraviolet radiation. There's UVC, which is very intense and very damaging, right? Fortunately, the stratospheric ozone layer, or the atmosphere as a whole, but the stratospheric ozone layer in particular, filters out all of that UVC. None of it gets through to the surface. It's a good thing, right? We would well, we would die. We wouldn't be able to withstand ultraviolet radiation at that intensity. UVB is a little less intense, and a little bit of UVB gets through to the surface of the Earth, a little bit, and then quite a lot of the UVA, which is still damaging, but it's certainly not as intense as either UVB or UVC, right? So when you go, for example, who's going to Miami? Jacob, I think you're going to Miami. When you're going to be a responsible person and put on sunscreen when you go to Miami, right? You'll be looking at the protection factor that the sunscreen has in terms of UVA, right? How much of that will it absorb and protect your skin, if that makes sense, right? And so this is the environmental human impact discussion, right? This is the ozone layer that protects us from ultraviolet radiation. It forms naturally, right, through oxygen being broken down, and the oxygen's forming with O2 to form O3, and it's destroyed naturally, right? And the issue is, are we doing anything here to disrupt this layer? That's why it's part of a class like this, right? So ozone spends most of its life, when we just go back to the formation and destruction slide here, ozone spends most of its life absorbing ultraviolet radiation. And by absorbing it, it breaks down that ozone and then quickly reforms, going through steps 2, right? And then it's broken down and it reforms, and it's broken down and it reforms. And by doing that, it is absorbing that harmful UVC and UVB radiation. Okay. All right. Makes sense. Okay, good. I think that's a good place to stop, everybody. I think that kind of sets us up for the next stage. So on Monday morning, I want to come back. I'm going to talk a little bit about how the story unfolded, and these two rather serious looking chaps here who discovered the culprit behind the human impact on the ozone layer, and then we'll look at the chemistry. And then we will be able to, after that coffee break on Monday, talk about climate change. We'll begin to introduce the big 800-pound gorilla in the room, so to speak. Any questions?